Welcome to the 11th session of our 3D Thursdays webinar series. I'm thrilled to have you with us today as we dive into the exciting world of additive manufacturing. Our topic for today's session is additive manufacturing, transforming manufacturing on the path to net zero. Discover how this session explores the transformative benefits of additive manufacturing with a focus on its pivotal role in supporting net zero ambitions and global decarbonization goals. It will feature a series of very interesting case studies on laser-based AM and wire arc additive manufacturing of advanced materials, showcasing cutting-edge work from leading laboratories, not just in India, but also Canada and the UK. These case studies will cover diverse engineering applications, highlighting technological innovations and practical outcomes. A dedicated Q&A segment will take place at the end of the presentation, but you can submit your questions anytime through the chat feature. I repeat, the chat feature. To ensure everyone has a chance to participate, we may group similar questions together. We'll address as many as time allows, so don't hesitate to share your questions. Lastly, please note that this webinar is being recorded. By participating, you consent to the recording being shared for educational purposes. Now, I would take great pleasure to introduce our speaker for today, Dr. Jinoop Arackal Narayanan, Senior Lecturer in Mechanical at Teesside University, UK. Dr. Jinoop Arackal Narayanan is a Fellow of the Institute of Materials, Minerals and Mining, Chartered Engineer, and a Senior Lecturer in Mechanical Engineering at the School of Computing, Engineering and Digital Technologies, Teesside University, UK. Prior to this role, he held positions at the Welding and the Additive Manufacturing Center at the Cranfield University and the Laser Additive Manufacturing Laboratory at Raja Ramanna Center for Advanced Technology, popularly known as Arackal, Indore, India. He leads the Laboratory for Advanced Materials and Manufacturing Processes at Teesside University. His research interests span additive manufacturing and specifically metal additive manufacturing, surface engineering, process structure property correlations, and deployment of advanced manufacturing for net zero applications. He has authored around 100 publications, including peer-reviewed journals, book chapters, and conference papers, presentations at both national and international levels. Notably, he authored the first comprehensive textbook on additive manufacturing in India, published by McGraw-Hill Higher Education for undergraduate and postgraduate scholars. In addition to his research, Dr. Narayanan serves as an editor and reviewer for several esteemed international journals, funding bodies, and conferences. He is an editorial board member of Research in Material Science, Frontiers in Manufacturing, and guest editor for several special issues. He is actively involved in collaborative projects on metal additive manufacturing with international universities, research labs, and industries. He is currently leading and collaborating on research projects funded by Royal Society, Innovate UK, UK Department for Science, Innovation and Technology, British Council, and the Lloyds Foundation. Let's welcome Dr. Jinoop as he takes us through today's presentation. Over to you, Dr. Jinoop.
Thank you. Thanks very much, Akshata, for detailed introduction.
Pleasure.
I'll share my screen now.
Sure. Yeah,
Okay?
Yes.
Okay, so good afternoon, everyone in India. So myself, Dr. Jinoop Narayanan. I'm a senior lecturer in mechanical engineering at Teesside University in the UK. So today's topic is on additive manufacturing, transforming manufacturing on the path to net zero. And it's really interesting that I'm back to Wipro 3D for a lecture because my journey with additive manufacturing started with Wipro almost 10 or 11 years back. And now getting this opportunity to talk for Wipro 3D as part of the 3D Thursdays is a great honor for me. So the topic for today is additive manufacturing, transforming manufacturing on the path to net zero. So first I'll start with some introduction about the university, then additive manufacturing, AM and net zero, some research case studies, conclusions, and what lies ahead. So and you can see some interesting cartoons which I have put in here, which are which I feel really interesting to see these cartoons related to 3D printing and additive manufacturing. The first one is 3D printing controls the supply chain, which is very much relevant to what we are going to discuss today because it brings whole supply chain to one particular machine or one particular industry. So that's the benefit of AM in terms of net zero. And again, the how the 3D printing is progressing, we are expecting that a human can be printed at some point by using 3D printing. So some of the content for this presentation is taken from this reference book, which was published in 2021 by McGraw Higher Education. And we are working on the second edition at the moment. So feel free to check for more information in this book and let us know your feedback, if any, from this on this book as we are working on the second edition. It would be really fruitful for us to include your feedback when we consider the second edition. So coming to the university, Teesside University is located in the northeast of England, and it is one of the young universities in the UK. It's a post 1992 university, and this is where the Teesside University is located in. And this is a town where we are in. It's a town called Middlesbrough. It's a port of town in the North Yorkshire, and it's south of River Tees, and it's part of Tees Valley region, which is one of the industrial clusters in the UK. And specifically, Teesside University, we have five different schools, and I belong to School of Computing, Engineering, and Digital Technologies, where we work and I collaborate a lot with School of Health and Life Sciences, also on the applications of 3D printing for life sciences application. And one of the major institutional research themes of Teesside University is net zero, and one of the three themes I will say. And based on that, we have established this center, which is a 13 million investment by the university, the government, and to create this net zero industry innovation center, where we work on different technologies related to net zero, like hydrogen, circular economy, smart energy, digital technologies, carbon capture, utilization, and storage. So these are the broader areas in which we work on net zero, and additive manufacturing is one of the themes that we work in this domain. At Teesside, we have a range of additive manufacturing systems ranging from polymers to composites to ceramics and metals. We have systems in DD, about material extrusion, but photopolymerization and different modes. And we have lasers that can we use it for surface treatments and surface engineering. And we are connected to Siemens connected curriculum, and we have the software packages that support the design for additive manufacturing and the toolpath planning using the Siemens connected curriculum. So coming to what is additive manufacturing. So I just wanted to, considering the audience, I just wanted to start with some basics and fundamentals, which is explained in our textbook, just for the wider audience to understand what is a technology. So additive manufacturing is a process of joining materials to make parts from 3D model data, usually layer upon layer, as opposed to subtractive manufacturing and formative manufacturing methodologies. So if you start dividing this definition into five different parts, it's a process of joining of materials. It starts from 3D model data. It uses a layer by layer build up approach and does not involve a subtractive manufacturing methodology and not involving any formative manufacturing methodology. So if you see any specific manufacturing process, and if the specific manufacturing process fits into these five categories, then we can call them as an additive manufacturing process. And there are different names, people call it in different ways: additive techniques, 3D printing, rapid prototyping, layer manufacturing, additive layer manufacturing, etc. But the ASTM standardized name for this technology is additive manufacturing, and the most commonly used layman term is 3D printing. So how does it connect? So this is something that I teach students normally to how to connect normal printing to a 3D printing. So in normal printing, you have a image or a file on your computer and which is fit into a paper. So you convert your image or the document into a paper and then you get it printed. While in 3D printing, instead of a computer image, we use a CAD model or a 3D model. Instead of a paper, we use a filament or a liquid or powder. And instead of a normal 2D printer, we use a 3D printer in this case. And instead of a 2D drawing, we get a three-dimensional product with us. So that's a basic difference between 2D printing and 3D printing. And it is similar to some things that happens in the nature, like the plant growth or the normal construction that happens. So everything happens in a layer by layer fashion. We didn't have the technology some years back, but now we are having the technology for using it for manufacturing. So what are the other benefits, or why is additive manufacturing or 3D printing really important? One is its complexity for free, because in conventional manufacturing, if the complexity of the part increases or it's more customized, then the cost of manufacturing increases. While in additive manufacturing, the cost is not a function of the complexity. It is almost independent of the complexity of the part, because that if the time remains same, the material consumption remains same, then the cost remains the same. But in conventional manufacturing, you need to build a different orientation. You need to have multiple equipments to manufacture a part. Then the cost of production increases. You can take this example of a complex part, which we have seen in the slide. So it's very difficult to manufacture these sort of component by using conventional manufacturing, mainly because of the intricacies involved in it. But once you start slicing them into different layers and see them in a layer by layer fashion, they are just lines or circles in 2 dimension. So uh, if you see the whole component in totality, it is complex. But if you start dissecting them into simple layers, then they are very simple designs in 2D sections. So that's what 3D printing does. And so it basically converts the complexity of the part of the design and simplifies into 2D sketches. And again, it reduces removes different stages in manufacturing, like documentation and drawing, tool procurement, raw material procurement, planning. All these stages are avoided in additive manufacturing as compared to conventional manufacturing. Other advantages, we can have multiple materials within the same part, that is material design freedom, where like in this particular case, we have copper and stainless steel, or copper or Inconel in this particular case. We have multiple materials in the same layer on multiple layers. I'll show you some of the case studies that we have done. Mass customization. So within the same build plate, you can have a number of parts and each of them can be of a unique design. Then again, integrated components. So another application is integrating sensors used during the manufacturing, which leads to smart components, which are integrated components, which can be used for real-time monitoring. These are used a lot in engineering applications where you need to predict the useful life of a component. So additive manufacturing can be used for such applications. And one of the areas that we are working on at Teesside University is also on making of smart components using 3D printing. And again, the next topic is sustainability. So this is something that we are going to discuss a lot in detail today. We'll come to that later. Logistics freedom, when you can design the parts in one part of the globe and it can be sent across and you can get it printed somewhere else. So logistics freedom is another part of 3D printing. So coming to net zero, we all are working towards a common goal of achieving net zero. Each country has its own goal. So what is net zero? So net zero means there are two aspects of net zero. One is to measure to lower emissions. So like you go adopt technologies which can reduce the emissions. and also use technologies that can remove the emissions like direct air capture or forest expansions, etc. So basically, we want to balance between the amount of greenhouse gases produced and removed from the atmosphere. So then only we can achieve the net zero goal. And in terms of UK, the net zero goal is by 2050. And if you start dividing that, the first goal is to get 50% emission reduction by 2032 and 75% reduction by 2037. And if you see in other country, different countries have got their own target for net zero. For example, India has got a new net zero goal of 2070, while UK is 2050. So most of the countries have got a range from 2050 to 2100 for their net zero goals. So this is something the world is working towards, and additive manufacturing also plays an important role there. And you can see that around 20% of the industrial emissions results in the carbon footprint, and almost 22% of the emissions comes from the manufacturing sector. So manufacturing sector plays an important role in the carbon emissions in the across the globe. And so emissions is something that we need to control. And if you start understanding the emissions in detail, there are different ways of classifying emissions. One is scope 1 emission, then scope 2 and scope 3. Scope 1 emissions are basically the direct emissions from sources owned by or controlled by a business, like basically the company owned vehicles, on-site fuel combustion, or industrial process that is generating the emissions. And scope 2 emissions are basically the electricity or the energy that the company is using. So the emissions that are produced by external sources but are associated with the business activities like the electricity, the district heating, or the purchase steam by the company. And the other one is scope 3, which is an indirect emission that occurs as a result of business activities that are not owned by the company or not controlled by the business. It's the most challenging to measure and most difficult to manage as well, because this includes the entire value chain of the business. It includes suppliers, consumers, and how a product is being used as well. It includes emissions from transportation, waste disposal, etc. And it is more than 70% of a company's emission, and it's most challenging to measure and manage. So if you start seeing what are the different scope 3 emissions, then we can see classify them into upstream activities and downstream activities. And if you go to the detail of that, some of them are purchase goods and services, capital goods, fuel and energy related activities, upstream transportation, waste generator in operations, business travel, employee commuting, and different ways like the processing of sold products, downstream transportation of the product. So these are the different ways in which the scope 3 emissions are generated. And the way additive manufacturing can support net zero is by control. One of the ways that additive manufacturing can control or reduce the scope 3, one of the ways additive manufacturing can help net zero is by controlling the scope 3 emissions. And these are the different ways. One is we can, in terms of purchase goods and services, we can have localized production, which reduces need for mass imports. So one of the companies that we were working with, they produce heat exchangers and they need to get parts from across the globe, different parts of the globe, different parts comes from different parts of the globe, and then they get assembled in the UK and for a heat exchanger application. This is one of the example. So in this case, if we have additive manufacturing in the company, then the heat exchanger can be produced in-house. So the inventory, the supply chain can be reduced. There's no need of inventory. Whenever it is required, we can go for the design and manufacturing of these heat exchangers. So there are different other examples where we are entirely dependent on supply chain. And as you know, supply chain disruptions happen every now and then nowadays because of the war and any other issues, and COVID was one of the example. So when we have such an issue with the supply chain, it's always good to produce parts locally than relying on the mass imports. So an additive manufacturing in one of the technologies that can support in that. Capital goods, if you go for subtractive manufacturing or other manufacturing techniques, we need to rely on multiple machines, multiple operations. While in additive, we can produce a part as it is in the single stretch in a machine, and then we may need post processing. But the entire number of machines that we need for the application is very less as compared to conventional manufacturing. Transportation and distribution, there is less need for international logistics and shipping from suppliers. Waste, as you know, additive manufacturing adds materials only at location where it is required, so it minimizes material wastage from the production. Then use of sold products. So again, if we go for light weighting, and I'll show that in the next slide. So one of the important application of additive manufacturing is light weighting, and light weighting allows us to reduce emissions, reduce the fuel usage, which is relevant in aerospace and automotive sector, even in any other sector, because transportation is sometimes a factor of weight, and if you can reduce the weight of a product, then it can reduce the emissions, it can reduce the cost involved. Then downstream logistics, we can have distributed manufacturing, which enables production closer to the end user. So these are the different ways in which additive manufacturing can be used for combating our scope 3 emissions. And as I mentioned earlier, one case is using additive manufacturing for weight reduction. So one case by Peter Burden is a 1 kg weight reduction could save up to $4,200 in fuel each year in aerospace. So 1 kg of weight reduction contributes to lower fuel consumption. It can reduce emissions and ultimately leaner operating model. So that's the benefit of using additive manufacturing. And you can see we can use topology optimizations. Topology optimization has been existing for a long period of time, but additive manufacturing allows this manufacturing of such complex designs so that we can use it for lightweighting applications. And they have been extensively used in the automotive sector and the aerospace sector, mainly because of the lightweighting capability that this technology has. Then now I'm taking one case study from one of the AM companies in the UK. It's called 3T Additive Manufacturing. Just want to take their case study because 3T Additive Manufacturing has set a specific goal to net zero and to achieve net zero by 2032. They aim to achieve net zero emissions by this year. And they did some initial analysis on how AM can reduce this, how AM can support net zero and how AM can reduce the emissions or material wastage. So when they start comparing this for making 10,000 components, by conventional manufacturing, 45 tons of material is being wasted, while by additive manufacturing, only 1 ton of material is wasted. And if you go to the fundamental raw material extraction in terms of mining, same components, we need 13,000 tons of extraction of raw materials for conventional manufacturing, while for additive, it is 45 tons. And again, if you want to, if you use additive manufacturing, we can reduce the carbon footprint of a part from 106 kg to 4 kg. So these are the different studies that they have done, and it clearly indicates that this technology has a lot to offer for net zero in terms of raw material extraction, in terms of carbon footprint, in terms of the metal wastage. And they have also set a three-tier strategy for achieving net zero. One is complete value chain, means focusing on sustainability across the entire life cycle of products, from raw material to end of life management. Then factory automation, implementing intelligent automation to improve efficiency. Digital integration, using digital technologies for real-time monitoring, optimization, and data-driven decision making. So so by using these three strategies, they're trying to achieve net zero by 2032. And their major mission is that every part produced within the company will be delivered with a net zero digital certificate and will be validated by an external body. So this makes a lot of difference to how we are thinking. There's a net zero digital certificate for a product when it comes out of a factory. And according to the CEO of the company, he emphasizes that manufacturers must adopt additive manufacturing and use net zero practice to remain competitive. So you can see the codes that he has mentioned. And as large companies push for sustainability across their supply chains to meet scope 3 emission targets, suppliers without clear carbon reduction strategies will risk losing business. And those who fail to act, those who are not interested to act on this and adopt the advances in technology, They may face carbon taxes, higher cost, or ultimately they may be replaced on the supply chain. So the message is very clear. Future proofing through AM and sustainability is urgent and essential. So these sort of digital certification for products, net zero digital certification for the products will force many companies to come forward, because you should have your sustainability targets or sustainability agenda to be in the market. And for this, you need to adopt advanced manufacturing technologies like this. And also we have Net Zero Technology Center in the UK, which works on industry emission reduction. And one of the major aims that they have put forward is reducing emissions from high carbon emitting industries like the oil and gas, which emits at least 3.4 gigatons of carbon dioxide a year by 20, and their aims to reduce it at least by 3.4 gigatons, which is almost 90% of the current emissions. And one of the projects that they are doing to support this is wire arc additive manufacturing, where they're using this technology for an oil and gas company, which I'm not showing in the slide, but they're using to this technology to print offshore components, rotating equipment, and build confidence in the technology for oil and gas sector. So this is how the things are moving on. People are adopting this technology more to achieve the net zero goals and for reducing the emissions. And the next, so so we talked about all these benefits of this technology, but we need to discuss the negative as well. We need to understand the limitations of the technology as well. So if you see the slide, um, if you start comparing additive manufacturing to conventional processes, there is an extra step always in additive manufacturing, which is to create this powder feedstock or the raw material required for additive manufacturing. So there is always an extra step associated with that. And so the metal ingots that are generally manufactured need to be melted, and then they need to be atomized to create this powder. So they need to be drawn to get a wire out of it. So this, and again, the process takes long time as compared to a conventional process. So if you take the printing time as well, the cost involved in additive manufacturing is higher as compared to a conventional process. So you can't always say additive manufacturing is good. There are challenges of using additive manufacturing because of this double step materials production and high energy intensive process. But if you start analyzing it further, if you see the conventional parts manufactured, there's a raw material production, product manufacturing, product use and end of life, and then it goes to recycling again. While in conventional additive manufacturing, we have this extra step of AM materials manufacturing. But if you consider the overall product life cycle, still additive manufacturing has got a benefit in terms of the product use. While in the raw material production, AM has got a high energy consumption. Material manufacturing energy consumption is more for AM. Product manufacturing also, we have a higher energy consumption. But in terms of product usage, we have some benefit. And overall, the graph shift towards having higher energy consumption for a conventional part. And we'll see how it is. So if you see a normal part and an additive manufactured part, you can see that the buy to fly ratio is significantly lower for an additive manufactured product as compared to a conventional part. So if you take an aerospace bracket as an example, the, the buy to fly ratio is 8 for conventional manufacturing. So while get if you use additive manufacturing, the buy to fly ratio is only 1.5. So then in that case, because of this higher buy to fly ratio, so if you can buy 8 kg of material, then you can produce 1 kg of final product. While narrative, you can use 1.5 kg of raw material to produce 1 kg of final product. So because of this high material intensive process in conventional manufacturing, the energy consumption has gone very high for conventional manufacturing. And so if you see, additive manufacturing has got a very high benefit over conventional manufacturing in this case. Again, if you optimize, so in this particular case, we didn't optimize the design for additive manufacturing. And if you're using additive manufacturing and optimizing the design for additive manufacturing, and you can reduce the weight of it considerably, that is 0.9 kg to 0.3 kg, then you have more benefits in terms of the product usage. So if you see, there's 24,000, the unit is kilowatt uh, per kg, yeah, kilowatt hour per kg. So we have 24 megawatt hour per kg as a savings when you use additive manufacturing, the lightweight additive manufacturing or the optimized additive manufacturing product in the product use stage. So this brings lot of benefits. So the same product is used, then we can have a very high level of cost savings, and then we can use additive manufacturing for that. So if you consider additive manufacturing for different products and different benefits. So this is one of the studies by Roland Berger, and he has provided for different parts on what is the benefit of this technology. So if you do take weight reduction is one of the benefits. If you take brackets as one of the example, how much of weight savings it is going to bring. So up to 120 kiloliters of fuel is saved per kg for reduction from 10 is to 1 to 1 is to 1. Then we have material recycling. We have specs custom IVR is an example where some of the demo pieces are getting discarded after a season. So we can customize the eyewear as per the requirement and then produce it. Then gas turbine parts or autoclave efficiency, reducing the number of parts in integration parts. You can reduce the number of assembly that is done for a product, and you can also buy spare parts, which is also a way towards reducing the reliance on the supply chain. So, what is a roadmap towards AM as a sustainable manufacturing technology? One is gain transparency of materials and process. So existing AM users receive no information about how large the environmental footprint of their AM part could eventually be. And we don't have much of information on the CO2 emissions that is generated during the production of the powder that is used for the process. So that is one way they need to work on. And other one is developing a suitable life cycle analysis database. So there's hardly very little literature available on a life cycle assessment of the entire value chain of additive manufacturing. So these sort of studies should be done so that we need to understand what sort of benefits this technology can bring. So one of the case studies that I have shown are some of the case studies that they have discussed in the literature, but we need to have more studies to be done to understand exactly what is the benefit of this technology for if you work on net zero. Then predict environmental impact before printing. So we need to understand, so there should be a need for a quick and easy tool or software program to predict the difference between an AM part and a conventional part with a high degree of certainty related to CO2 emissions, which will help us to understand whether we need to go for AM or not. So that's another thing that we need to work towards in terms of research. And after gaining transparency, the real work starts, that is mitigating AM harm to the environment. So additive manufacturing was not initially considered as a green technology when it was found in 1986. It was a technology that was used to create complex shapes which were not possible with conventional manufacturing. But with the advancements in the technology, more and more more and more advancements happened, like process monitoring, real-time control. So we need to develop technologies which can be used for reducing the environmental impact of this technology to minimum. So this is another work which I took from one of the case studies that is reported by MTC in the UK. So if you take the whole powder powder bed additive manufacturing, there are different ways in which we can work on sustainability or achieving net zero. One is chasing the energy supply, life cycle analysis, design simulation optimization. We can recover the consumables and use them. Powder recycling, waste heat that is being generated can be recycled. Then powder rejuvenation, you can use plasma technologies to spiritize the powder again and then use it again. Then like material labeling is another way. So different ways there that we can work towards achieving sustainability with additive manufacturing. So again, using AM for hydrogen economy, that's another way in which we work towards we can use AM for net zero goals, because hydrogen is one of the commonly used fuel nowadays, and it's a lot of need of using hydrogen in terms of natural gas, and a lot of efforts is going across the globe. So using additive manufacturing for hydrogen storage. So we are also working on similar projects using additive manufactured materials, understanding how they behave in hydrogen environment. So we work in with our net zero center. We have a reactor which we can expose the materials to a higher temperature and pressure in hydrogen conditions, and then we test the materials and how they behave. One of the PhD students project. So another study which I've observed from a study in Germany is using hydrogen reformer that uses multiple materials to convert methanol or ammonia into hydrogen. So this involves a lot of pressure reduction, high reaction temperature, high temperature differences. So you need metals to ceramic within the same part. So the hydrogen reformer is made by using additive manufacturing for a green hydrogen production application. And another way, like how AM can support net zero, is circular economy. So, the 4 Rs: one is reduce, reuse, recycle, and recover. So, in additive manufacturing, we have opportunity to reduce, design, and plan for reduced resource consumption, reuse existing parts and extend their life, and recycle the materials and that can be used for the process again. So, so the reduce is basically the design and planning for reduced resource consumption, while reuse means extend the product lifespan. So basically, we use DD technologies for recycling and reusing the parts or remanufacturing the parts. We'll come to that next slide. If you see this particular chart, pie chart, we can see how that work is going on in additive manufacturing. Circular economy based research goes a lot in additive manufacturing, and most of the research is focused on material extrusion, which is FDM, and the most expected out of it. And then the next one is powder bed fusion, and next is DED, and very limited studies on binder jetting and wet photopolymerization. And exactly, there was no specific studies on material jetting or sheet lamination. So a lot of research is going on in this direction, basically to reduce the usage in design stage and production stage. So like in design stage, we have options of using continuous printing. We can reduce material by using recyclable materials from nature, thermosets. Then we can use topology optimization to reduce enclosed voids. Enclosed voids trap the powders a lot, so we can have voids which we can design the product in such a way that the powder can be easily recovered from the product. Then we can reduce overhang so that we can try to optimize the overhang required for a design, so that we can reduce the reliance on overhang structures and then reduce the material usage. Production planning, again, reduce build orientation, curing time, capacity utilization can be used for energy reduction. We can control the environmental impacts, and then we can reduce the material wastage as well. In terms of reuse, there are two ways that people look at it. One is repairing, another one is remanufacturing. And the most commonly used technology for that is directed energy deposition, or DED, where we have an original part and then it used for some time, it is worn out, then we can, or damaged or worn out, and we can directly process on that and produce a new part which can be used, or repaired product which can be used for application, which is extensively researched for turbine blade applications or also used for tooling applications. Then the other side of reuse is remanufacturing, where we have original product which is either worn out or discarded, and then we can use AM to generate a new product out of it. Either it can be the same as the original form, or it can be a new product out of it. But we don't have to start from the scratch. We can use an existing product and use that as a substrate material and start building around it. Then recycling is another way. A lot of recycling based research has been happening in additive for plastic, metals, and composites. Also, powders are being used. So you can see in this particular case, one of the studies where they use uh, inductively coupled plasma process to recondition the powder. So this was used powder. Then they use reconditioned powder for manufacturing, and they could hardly see any difference in the properties. There are minor deviation in the mechanical behavior. And there are also studies where people convert this scrap material or the powder material to wires. So there's one of the study that is done in Sheffield University, where they have developed a technology where it's called conform. So it uses powder as a feedstock, or the machining swarf can also be used as a feedstock, and then we can extrude it out as a wire form, which can be used for wire based additive manufacturing. So this is the first part of the talk, and the next part is some of the case studies which I'll just go through quickly on how some of our research were working towards net zero and the net zero goals. So one of the first case study which I want to show is the one that I did at Arackal, where we did laser DED of Hestalo X, which is for a supercritical CO2 cycle application. So we used a 250 by 250 by 250 2 kilowatt fiber laser with a CNC manipulation and a dual powder feeder. So this was the application. So we wanted to develop a heat exchanger that can be used as a primary heat exchanger, which can take the heat from the nuclear side, from the energy side, and then transfer it to the power generation side. So the material that is identified for this was Hestalloy X. It's a nickel-based superalloy. And when we started working on this, there was no literature available on this particular material. And it's very difficult to process this material because it has got extensive cracking tendency, and there's no literature available as well. So this was a final product that we developed, final prototype that we developed, and for the research, I hope the research has moved forward with that, but I stopped with developing the manufacturing methodology for making this heat exchanger. So it started off with single lines. As we normally start in additive manufacturing, we started with single lines at different process parameters, generated a single lines, and then we developed the process window and develop the window of laser energy per unit powder feed, which is a combined process parameter that we use for developing the window. And we could identify a range of parameters that could lead to continuous deposition without any cracks. And we correlated it to the energy density that is being used for the process. And then we used it to develop wall. So if you see this, observe this heat exchanger very closely, it has wall structures as well as bulk structures in between. So we did some systematic investigation on wall as well as bulk structures. So we studied the wall structures in the beginning. So we did studies at different parameters, different energy densities to understand how a stable wall can be generated by using DD technology. So the major challenge here is the balance between the Marangoni effect and the viscous forces that acts during the process. So we need to find that specific process window, and even we tried different trials by varying the delay during the manufacturing. We incorporated delay during the printing between the layers, and so that we can control the energy that is accumulated, which controls outward flow of the material. So this study was basically done to find that optimum range of parameters that we can use for the wall structures with optimum geometry and optimal material properties. And again, then we went to the bulk structure. So we deposited different types of bulk structures at different parameters, different energy densities, and we could find an optimized bulk structure which has more, no, close to 99.5% density. We didn't observe any specific cracking in this optimized condition, and the grain structure is mainly cellular in nature with some secondary branching in the top layers, mainly because of the variation cooling rate as we move from the bottom to the top layers. And we could also see variation in the grain size as we move from the bottom to the top layer, basically because of the variation in the heat cooling rates, because of the heat transfer mechanism that is happening. And then we did EBSD. We could observe a grain growth, preferred grain growth in the 100 plane observed typically for nickel-based alloys. Then we could see the mechanical properties which are higher than the conventionally built samples, but slightly lower than the powder bed fusion samples, mainly because of the higher hardness that is observed for the powder bed fusion sample and the fine grain structure that you observe for powder bed fusion sample as compared to the DED samples. Then even the mechanical properties, DED is slightly or inferior to as compared to powder bed fusion, and it is superior than the conventionally built samples. But if you consider that ductility as an important factor, then DED conventionally built samples are superior as compared to both DED and powder bed fusion. So we had certain issues. One is the non-homogeneous microstructure. We had microporosities during the manufacturing. So these needs to be taken care of. So we used a method called in situ sequential layer by layer remelting, where we did remelting during the manufacturing itself, which was recently published in International Journal of Advanced Manufacturing, where we use this laser scanning to control the porosity and control surface roughness and the microstructure. So we could get close to 100% density, the RA value reduced significantly. We could refine the grain structure to some extent, and we could reduce even the grain orientation or the grain growth orientations. Okay. And the other study that we did was on heat treatment of these materials, basically to get refined or the homogeneous grain structure, or as opposed to the refined grain structure that we observed in additive manufactured parts. So we got recrystallized grain structure at solution treatment, and then we compared it with the mechanical, and we could bring the mechanical properties very close to the conventionally built parts. And then we did an attempt to make a heat exchanger using a three-axis configuration using DEDs. Very challenging to make a heat exchanger with a three-axis configuration. So we did different trials, different challenges. Optimizing that sweet spot of process parameters is really challenging. So we did a lot of challenges, and then we developed the program, and then we developed the proof of concept, and we built this heat exchanger, which is 200 by 200 by 200 millimeter cube size. And the other case studies I'm just going through quickly in the interest of time. But if you have more, if you need to have more details of this, you can contact me, or you can even look into the publications that is referred in the slides. So one study is on functionally graded materials, where we try to join copper and nickel, which is for IIT Kanpur and IPR, where we try to develop the graded copper and stainless steel joint. Other study was Dulero 50 and stainless steel. In this, what we did is we mixed the powders in advance, and then generated the structures by gradually changing the composition from one end to the other end. So the composition was 0% stainless steel at one end, the other side was 100% Dulera 50. So we could get gradual change in composition, as you can see in this diagram. The gradual change was observed, and the gradual change in mechanical properties were also observed in this case. Then also recently, one of my previous colleagues, Sunil Yadav, we worked together on a project on using copper stainless steel FGMs. So it's really challenging because of the poor solubility and immiscibility in liquid phase of copper and Fe, and again rapid solidification LDED results in randomly distributed phases, phase separated morphology in the melt pool. So trapping and segregation was observed a lot. We could see a lot of cracking, and the cracking tendency reduced when we increased the copper composition, and the cracking behavior also changed with respect to the composition of the material. It it was tearing at some part, and it was also porosity induced cracking at some point. But if as the copper composition increases, more liquid film is available to fill the cracks, and we could reduce the cracking to some extent. Also, we did similar studies on copper stainless steel wall structures. The copper stainless steel joint was direct joint was made, which was defect free. But if we went when we went to the 20% graded structures, we could see that a lot of defects were observed in the samples, micro cracks were observed, and we could see that the mechanical properties reduced significantly because of the higher thermal stresses or thermal cycling that is happening during the process. We also used laser surface melting as a polishing technique. So this is also one of the methods that we didn't wanted to go for mechanical polishing of AM parts to reduce material wastage. So we use laser as a tool for polishing the material, and we could reduce the surface roughness significantly by using a continuous wave 50-watt laser power to reduce the surface roughness. So we could generate a lot of correlation with respect to the melt pool depth and surface roughness, and we could also correlate the energy density with the surface roughness, and we could divide the regions into shallow surface melting and surface over melting, and we could clearly identify which region we need to focus, or which energy density that we need to focus to get a desired surface quality. So the next one is more the work that we did at University of Waterloo. So this is a 1 kilowatt fiber laser, which is used for the DED process using a powder as a feedstock. So we did works on overhang geometry like dome structures. We did the toolpath planning for this, and my involvement was more into the process and characterization part of these structures, while my colleague Fazane Kaji, she was the lead author in this particular paper. She was involved in developing the toolpath and developing the algorithms for this. So we were working on developing this DOM structures, processing of this, and characterizing and qualifying them for different applications. So we could see that the DOM structures that we built are defect free, and we could also see that the geometrical quality is also very high. This is one of the interesting works that we did and published in Additive Manufacturing Journal, which is on developing overhang geometry like a double bent pipe using additive manufacturing. So we could see that when you slice this particular geometry, one region has got a lower layer thickness, another side has got a higher layer thickness. So just by controlling the scanning speed within a single layer, we can control the material deposition or the quantity of material deposited, and then we can use it for controlling and making these sort of a bent pipe structures. So we use lower scanning speed at one region, we could use a higher scanning speed another region. So we did some sort of material analysis to understand if this has an impact on the properties. So we did CT analysis, we did material analysis and geometrical analysis just to ensure that the properties are at par with what we are expecting and there is not huge deviation because of the variation in scanning speed within a single layer. And we could see that the mechanical properties are within a range. The structures are largely defect free. There is no huge variation in the defects that is formed in the process. Another challenging and important work that we did was on a cladding application for a nuclear sector. So we did a cladding on a zero point 0.5 millimeter thin tube. So this is for corrosion resistant application for a small modular reactor application. So it's more towards the nuclear energy side. So we had to develop a coating which is highly corrosion resistant and oxidation resistant. So because of the thin thickness of this or the limitation of thickness of this tube, it is really challenging to develop such a coating. So we had to develop a process of external cooling, and we did a lot of trials. So this is how we started with. We damaged the tube a lot with the initial trials, but as we moved forward, we could optimize the shielding gas flow rate and we can control the cooling, because when the laser touches the surface and if it is only 0.5 millimeter thick, the tube gets damaged within a second. So it's very important to cool it suddenly. So it's very important to have a very fast cooling, very fast scanning speed as well, because we should not allow the laser to reach or react at a particular point for a short longer period of time. So a lot of factors to be considered in this particular case to develop a process window for developing this cladding. So we developed this, and then we could observe very good bonding between the tube and the clad regions. And you can see how the different zones can be classified here. So there's a tube region, there's a mixing zone, and the clad on top of it. This is another more simple example which I wanted to show the turnaround time in which additive manufacturing can work with. So we use this technology, DED technology, D, sorry, DED technology to damage a tool steel part which was developed in the assembly. And this part got damaged during the assembly process, and we were asked to develop and repair this, and which was done in a turnaround time of 24 hours. Then another work where we work on using deep learning techniques. So we use DB scan for unsupervised learning, and then RandLearn as methodologies to develop a deep learning technology for predicting the deviation in the actual part and predicted part. So we use laser line scanner, scanned the part and generated the powder scan, sorry, the point cloud from this. And this point cloud is used to predict, is fed into the point cloud data is fed into the deep learning, and first in the unsupervised learning and then supervised learning, uh, to generate this sort of predictions on how we can predict the deviations with that is developed during additive manufacturing. And the next step of work was to control this deviation. So we could predict it, now how to control it. So this was an algorithm that is developed by one of my colleague Farzan and Kaji, where we developed this algorithm to develop, and we could control the scanning speed and control the laser power during the manufacturing in such a way that we could achieve a flat surface. So this is the original structure, and what once we could adjust the scanning speed and laser power, then we could get flat surfaces with a higher quality. So this is then, as we are controlling the scanning speed during the manufacturing and we are controlling the laser power during manufacturing, it's very important to understand whether this is having any bad effects on the final product. So we did quality control checks, we did the cross-section analysis, we did the CT analysis of it, and we could see that largely there was not huge impact on the defects that is formed. In fact, there was minor defects in the laser control samples, but largely it was defect free. And we could not see any huge variation in the grain structures as well. I'll go through quickly. So the next work is on Inconel 617, a similar work that we did for Hestlo eggs, which is in the in progress at the moment. So we are working on the characterization of this for publication. So we did a lot of effect of energy density on the defect formation. So there's a CT scan results and the microstructure analysis, which is mainly to which shows that at lower energy density we got a very fine grain structure, lower angle grain boundaries, and a higher angle grain boundaries, higher concentration of higher grain boundaries. And again, we got a very high hardness as compared to conventionally built Inconel 617 samples. But most of the samples has got cracking, but we could avoid cracking in some of the conditions, which was not reported in this particular work. And one of the recent works that we did as part of a UK Iceland project is exposing hydrogen to a 3D printed nylon part. So we 3D printed nylon, and then we used our facility Net Zero Center to expose the material to hydrogen conditions. So in this case, I think we use 100 bar and 72 hours for for exposure, and you could see how the samples have become after hydrogen exposure. We could see the bubbles, we could see the hydrogen trapped into the material, and we could see reduction in the mechanical strength and the modulus after hydrogen exposure. It's mainly because of the change in plasticization and hydrogen-induced aging effects that has a reduction into the breaking of the chemical bonds to some extent. But we are still working on further on this because this is one of the studies that we did. We are still working on to understand more in depth on how we can control this or how can improve the hydrogen exposure resistance of these materials. So we observed that the reduction in shore hardness and the flexural strength was also there, and we could see a lot of voids and particulates in the samples. And we did a life cycle assessment as well, a quick life cycle assessment from cradle to gate, and we compared a conventional nylon to 3D printed nylon and how which can be beneficial for a transportation application. And we could see that in terms of material usage, 3D printing is better, but in terms of the energy usage, extrusion, conventional extrusion is better. CO2 emission based also, if you consider the filament and the overall life cycle, extrusion is better. So if you consider the environmental impact, it again depends on the context. So it's moderate for extrusion, slightly higher for 3D printed nylon. This is our initial assessment. We are still working on it to develop a full all developed uh, full scale model on life cycle assessment of 3D printed nylon. So coming to the final part of it, so challenges and opportunities in AM. There is a need for lot of challenges in shortage of qualified materials, speed of productivity, repeatability and quality assurance. Industry-wide standards are required, end-to-end workflow integration. We have software limitations, security issues, and skill set gap. That's why we are conducting these sort of events and webinars. Opportunities, machine and software development, process development and control, material feedstock development, design for additive manufacturing, modeling and simulation, characterization and testing, quality control and assurance, application development, education and training. So these are the different opportunities that are there in additive manufacturing, but still a lot of research to be done. Our group specifically now works on using additive manufacturing for net zero application, using lightweighting, using for hydrogen applications, circular economy applications, and also using for nuclear and aerospace applications. So in conclusion, AM is an advanced process used to build components, started with rapid prototyping to metal AM now. Careful material and process selection is necessary for successful AM implementation, which you might have seen in the case studies. We need to have systematic investigation, training for high quality parts, and research opportunities are still plenty to improve the process. These are some of the special issues which I'm editing at the moment. So if you are interested in contributing your work, feel free to contact us. So it's on Sustainability Journal, and this is a new journal that we recently started, and I'm editorial board member for this journal, which is Research in Material Science. So if there is any research you'd like to share, feel free to submit your research to this. And I'd like to acknowledge my students, Robin, Zakaria, Sam, Aishwarya, and Ajita, who are supporting me in this sort of works. My colleagues and team members at Teesside, Tariq, Usha, and Jeff, and collaborators, Professor C.P. Paul and team at Arackal, S. Santosakani, Professor S. Santosakani, and Dr. Fazana Kaji from Waterloo, Dr. Sunil Yadav from Nottingham University, Professor Helen and team from Swansea University, Professor Arun and team from Wolverhampton University, Denny John from Florida International University. And I would like to thank my funders, British Council, Royal Society, Department for Science, Innovation, Technology, DAE in India, and FedDev in Canada. Thank you.